Welcome to T2, day 17 of calculus. We will be continuing our fun with related rates. I know you didn't think that was possible, but yes, we're going to have even more fun with related rates. Before we even read the problem, please write down those three words: picture, know, and want. So what do we have here? It says Kathy, who is 5 foot 9 inches tall, so there's something that's important, 5 foot 9 inches tall, is walking towards a 23-foot street lamp at a rate of 5 feet per second. How fast is her shadow shrinking when she is 9 feet from the lamp? Well, our picture is going to look something like this. We have a lamp up here. Yay, you know, you love my pictures. It's 23 feet tall. And Kathy here, and again, my stick figures, as you remember, are really awesome. She's 5 feet 9 inches. That's 5.75 feet. That's important. And the light is going to be shining down. Where's her shadow going to be? Her shadow is going to be right here, that distance. So let's call the shadow distance S, and let's call the distance she is from the lamppost X, like that. So what do we know? Well, the 23 feet and the 5.75 feet are written in there. We know that Kathy is walking at a rate of 5 feet per second toward the lamp. Towards, that's important, towards. So dx dt, the rate of change of x with respect to time, is negative 5 feet per second because it's getting shorter. She's walking towards there. What do we want? How fast is her shadow shrinking when she is 9 feet from the lamp? So we want ds dt, and that should be negative, when x is 9 feet. So we know something about dx dt, we want something about ds dt, so we need a relationship between x and s. So we need our equation to link together x and s. This is where it gets pretty fun. We need to come up with a relationship, and this is going to have to do with similar triangles. And the similar triangles are the following. There is this triangle right here, and that triangle, that purple one right there, is going to be similar to this one right there. So what does that mean? Corresponding sides, the ratios will be the same. So what that means is this side to this side is the same as this side to this side. The same corresponding relationship should be true because they are similar triangles. So what does that mean? It means that S plus X over 23, that's an S and an X right there. S plus X, so the base to the height here, is going to be the same relationship as the base to the height of the smaller triangle. What's the smaller triangle base to height? Well, that's S. And what's the height of Kathy? Or what's Kathy's height? 5.75. So there is our relationship. What does that tell us? You cross multiply, and when you cross multiply this, you end up with 23S is equal to S plus X times 5.75. That tells us that 17.25S, you do this out, so you FOIL this out and then you subtract, is going to be equal to 5.75x. That's our relationship between the two variables. That's our relationship. It's pretty straightforward. Both of them are linear. After we have our equation, we need to differentiate. So when we differentiate this, we end up with 17.25, not an S, ds dt, because we're doing it in terms of t, is equal to 5.75 times dx dt. And which one do we want? We want ds dt. So we need to take the dx dt and plug it in. We end up with 17 that's a 25 right there. 25 times ds dt is equal to 5.75 times dx dt, which is negative 5. So you know, therefore, that ds dt is equal to negative 5 times 5.75 over 17.25. And when you do that out, you end up with negative 1.66 repeating feet per second, because this is the length of the shadow. And it should be negative because it's getting shorter. The key relationship here is the similar triangles. Remember, here's the big triangle right there, and that triangle is similar to this one. So therefore, base to height, the base to height ratio will be the same for each. So the key to this entire problem was right here. We didn't use the Pythagorean theorem. We used similar triangles. So picture, know, and want written down before we even start the second problem. A rectangular pool 20 feet deep with a base 10 feet by 12 feet is being filled with water at a rate of 20 cubic feet per hour. So what do we have here? We have this pool. It's rectangular. And what does it tell us? It tells us that it's 10 feet deep. It's 20 feet deep. So these are 20 right there. 20 feet deep, with a base that is 10 feet by 12 feet. This is not to scale. It's not to scale. So 10 feet by, not 10, 10 by 12. So here's our pool, not to scale. That one's 12, this is 10, and it's got a depth of 20. It's being filled with water at a rate of 20 cubic feet per hour. So dV dt, the change in volume, dV dt, it's being filled, is at a rate of 20 feet cubed per hour. It says, at what rate is the water level rising? At what rate? And it doesn't specify time, so it's going to be the same everywhere. So the water level at a certain point, like the water will be filled at to a certain height like this. So that height, let's call it x, or h. You can call it x or y. Let's call it height, h. So we want dH dt. We just want dH dt. It's going to be constant because of the shape, and the volume is going at a constant rate. So when you do this, we know we need to link volume and h. Volume and h. Volume and h. Well, the volume of the water is just going to be, oh, not highlighter. The volume of the water is going to be, and it's, again, it's a rectangular shape here. So it's going to be base times length times height. Well, the base, that's going to be our b, and this is going to be our L. So you end up with a volume is equal to 10 times 12 times the height, which is changing. So what do we have? We have volume is equal to 120h. So we have our equation. Now we need to differentiate with respect to time. So when we differentiate with respect to time, it says dV dt is equal to 120 dH dt. But we specifically want dH dt, so we need to find a value for dV dt. Well, it tells us dV dt is 20 the entire time. So that means that 20 is equal to 120 times dH dt. So what does that mean dH dt is? 20 over 120. So dH dt is equal to 20 over 120, and it's a change in height, so it's going to be feet per, and it's minutes in this one, which is 1 over 6 feet per minute. And you'll notice it wasn't at a specific time because the height of the water is changing the same amount every second. And before I forget, let's go to the second part here. 12 feet from the lamp. If you wanted 12 feet from the lamp, instead of plugging in the 9 feet like we did before, so where did we get 9? We plugged in 9. Well, where did we plug in 9? It's really interesting here. We didn't have to plug in 9 anymore. It's interesting. So the shadow is decreasing at a rate of 1.6 feet per second, regardless of where she is. So the answer to the second one here is also going to be negative 1.66 feet per second, because look into here. Did we have to use this 9 anywhere? 9 wasn't needed. The length of the shadow, how fast it's changing, is independent of how far she is from the lamp. It's pretty cool. Like down here, we didn't need a time for this. We didn't need a time just because dH dt was changing the same amount everywhere. Same amount everywhere.